So as I mentioned, we'll be interested in understanding and bound the expected value of the spectral norm of random matrices. And one of my favorite, so now I'm going to talk about one of my favorite inequalities. It's a matrix concentration inequality. It's known as non-commutative kinship. This is the theorem. So this is what we call NCK, where it stands for non-commutative kinship inequality. So what it says is that the idea is to, so we call this non-commutative kinship. So the idea is to control the expected value of the spectral norm of random matrices. But in this inequality, we're not going to have the matrices they're not going to be just random matrices. They're actually going to be deterministic matrices with random coefficients on it. So we're going to have A1 through AN, they're deterministic, right? Deterministic. And symmetric matrices, symmetric D by D matrices. Right? And G1 through Gn, they're going to be IID standard Gaussians. Okay? And we'll control what we call the Gaussian series. Right? So sum of GK AK, okay, from 1 to n, right? This is a random matrix. It's a sum of random matrices, right? The randomness comes just from a coefficient, but the way that these matrices are different, right? There's some interesting interaction happening. And we want to control, right? This matrix we sometimes call X, right? We want to control this random matrix. We want to control the expected value of the spectral norm. Right? And so the expected value of the spectral norm, as we'll see, will be smaller or equal than basically a logarithmic factor, which was that because of that d. Remember, there was this square root of the factor. So I'll put here, I'll keep track of all the constants. Right? So with all the constants, this is 2 plus 2 log of 2d square root. Times, maybe I'll erase this, I don't need it, times a parameter is sigma, right? And the parameter is, oh, here the square root is outside. I mean, if you don't care about constants, it doesn't matter, but if you care, yes. And this is the variance parameter, right? And the variance parameter is exactly as before, right? It's the spectral norm of the sum of the expected values of these squared, right? But these squared, the Gaussian becomes 1, and so we just get, it no longer is a random quantity, we just have, right, the expected value of there's no expected value because the expected value of the Gaussian is just 1, we just take the spectral norm of this sum. Okay? And so this is non-commutative kinship, right? And up to this log factor, this is essentially tight. Right, because again, okay, maybe I will call this x. Right, this quantity here, the sigma squared, basically is, right, what is it? It's the spectral norm of the expected value of x squared. Right, so if we put, right, the expected value of x squared, what we have expected value of these sums, right? And the expected value of these sums, all the cross terms are 0, so we just recover the terms squared. We get a 1 from gk squared, and we get ak squared, so it's exactly this. Right? And of course, you know, this is by just Jensen. This is of course smaller than if I take expected value of x squared. Right? And by, you know, if we believe concentration and all the things we were saying about how this is a high-dimensional quantity, so we should see a lot of concentration, then this should roughly be the square of the expected value of x. Right? And Jensen would give a relation between the two, and there's ways of getting relations out of the way, and so on. But this is, so which means that sigma is right of the quantity. It's at least, should be a lower bound to this quantity. And so this is, at most, it's off by this extra logarithmic factor. And we'll spend, I mean, I myself have spent quite a bit of time thinking about when is it that this logarithmic factor actually belongs, when is it that it doesn't. So we'll spend some time talking about this. Yeah, but so this is sort of the right variance parameter, as you can see here. And now the question is, where is this term coming from? What is it saying, and so on. But let me first, before we even go into into anything else, let's use this inequality to get a tail bound. Right? So we said that Gaussian concentration gives you a tail bound, so let's try to use Gaussian concentration. Right? Okay, so we can use Gaussian concentration. Right, so what does Gaussian concentration give us? Well, we need to define a function. It's clear what the function should be here. Right, the function f should receive the Gaussian vector and should give the spectral norm of the sum of gk ak. Right, so then the value of f is exactly the term we're trying to control, and the expected value is exactly the thing we already have the control for. Okay, so now we have to compute the Lipschitz constant. Right, so the goal now should be to compute, we need to compute the Lipschitz constant. Okay, so let's do that. So let's say that we have f of g, right? Let's say that we take f of g minus f of h. Right? This is what? I mean, for now we're going to need smaller equal. Let's work this out. Right? What is this? This is equal to spectral norm of the sum of gk minus hk, ak. Right, but now what is the spectral norm? The spectral norm is the maximum over vectors v that have norm 1 of v transpose this sum of v. Right? But now I can move the v inside because it's linear. This v is linear. I can move it inside, right? The same thing with the one from this side, and I can pass it, make it pass the gk's and the hk's because it doesn't it doesn't depend on v, that part. Right? And these are just scalars. So I have this being equal to, okay, let me go all the way over here. Right? This is equal to the max. Right, of, let me do this, maybe you can see better, v having norm 1, right, and now what we have the sum of gk minus hk, and then v transpose ak v. Okay, so now we have Cauchy-Schwarz again, because all this is an inner product. Right, this goes from k1 to n. This is an inner product between these vectors gk minus hk, the vector whose kth entry is gk minus hk, and the vector whose entry is v transpose akv. Right, so again, Cauchy-Schwarz. Right, so Cauchy-Schwarz, what does it give us? It gives us that max of v now with norm 1, and we get exactly the norm of g minus h, and then we get the norm of these. Let's maybe keep track of it. So square root of let's see if I can see still well. Okay, maybe this is better. Of the sum, right, from k from 1 to n of v transpose ak v, right, is the ultimate norm of this vector squared. Okay, and of course, the max can move past here, right? So I don't have a lot of space, so I'm just going to do this. Right, this max can certainly move here. And so it means that the Lipschitz constant for this function, right, is just given by this quantity. Right? So this motivates us to define a new variance parameter. So we're going to call this the weak variance. Right, and the weak variance will be this parameter sigma star square is equal to sum or max v1 of the sum from k from 1 to n of v transpose ak v squared. Right, this will be a different variance parameter, and essentially f is sigma star Lipschitz. right? So we compute the Lipschitz constant, like it is f, right? Now I can change, I can say this function is sigma star Lipschitz, right? So, right, because now this is exactly the inequality we have, right? This difference is smaller or equal than, the norm times this constant exactly, or, the square root of the square of that. Okay, so now that we have this, let's use the Gaussian concentration. What do we get? We immediately get a bound. We immediately get a bound on this, on the spectral norm of the Gaussian series, right? And the bound will be that the probability, right, that the spectral norm of this series, right, is bigger than right, the thing we control it, this mean, right, because I only have an upper bound on the mean, I can only get an upper bound on the tail here. T sigma, right, plus T. This is smaller or equal than, right, this is smaller or equal than now the e to the minus t squared over 2. So let's push the sigma star here. So let's do a change of variables. So we'll do a change of variables, right? This will be our new t. So if we do that, we get that this is, okay, right? This is now smaller or equal than exponential of, I believe, minus u squared over 2. Right? Okay, so immediately you get a control on the tail, right? It says the probability, right? The true value or the expected value is bounded by this, and the fluctuations are controlled by this other parameter, sigma star. And so if you have both parameters, then you can bound just take u to be any number. It doesn't even need to be very large, just reasonably large, and you already get a very small tail. Right, so from this control on the expected value, all you have to do is control this quantity sigma star, and you get immediately a bound on the tail. And what I'm going to show you now is actually that sigma star is smaller than sigma. So you could replace sigma star by sigma, and it would still be true. There still would be a weaker inequality, right? So you wouldn't even need to control this other parameter. Okay, so we'll see that sigma star is smaller than sigma, that this weak variance is actually smaller, meaning that, right, that this inequality is still true if I replace sigma star by sigma. But in general, sometimes sigma star is actually a lot smaller, and this is important. Okay, so let's see the proof that sigma star is smaller than sigma. Right, meaning that the deviations that you see are actually even smaller than the, not just because of this logarithmic factor, but the variance parameter of the deviation is in general smaller than the one for the mean. Right, so that another way of saying this is that, another way of saying this is that in order to control the deviations of a variable like this, it's not in terms of it's like bigger than twice its expected value or 3 times its expected value, but it's more in terms of it's bigger than its expected value plus a little bit, right? This is the scale. The scale of the fluctuation is a lot smaller. Right, so let me write sigma back here, right? So sigma was, and sigma squared was the spectral norm of the sum of the ETH squared. Squares here. Right, and so we'll prove, right, superposition, sigma star is smaller or equal than sigma. Let's do it in terms of the square, and this will also be a simple application of Cauchy-Schwarz. Okay, so let's write the definition. So what is sigma star? Sigma star is the max. V having norm 1 of right? So we have the sum of this. So okay, so we need to write everything out first. Okay, so k from 1 to n. And now the trick is just to do Cauchy-Schwarz inside the square. Okay, so again, Cauchy-Schwarz. That's a Cauchy-Schwarz inequality inside the square. Okay, so because why? Because we can think of this as the inner product between V and AK. Right, so we can think of this as a vector and this as another vector and do Cauchy-Schwarz there. So let's try that. So we get max k from 1 and now sum k from 1 to n. And inside the square, what we have norm of V, norm of A, k, B. Right? This is just Cauchy-Schwarz inside. Now norm of V we know is 1. So what we get that this is the same as max V 1 of sum from k from 1 to n of, right? So now let's write this out because the norm square is just V transpose AK square, right? Because it's AK times, it's V transpose AKV, but A is symmetric, so we get exactly this, right? And now the V can come out outside of the sum. Right, and this is exactly sigma squared. Right, so sigma star square is smaller or equal than sigma squared, so we prove that these are small, right? So I mean they're all non-negative, so I can take away the squares. So this is true. Okay, so in particular it means that the fluctuation, I mean it might be the same scale, right? But every time you have a control and expected value of the spectral norm, right, at least in these for these Gaussian series, then you can definitely control, being twice as big as the spectral norm 3 times, 4 times, 5 times, we'll start having an exponential decay on the probability, right? But oftentimes you even get a control that's much better, right? And I mean, you would have the log factor too, so you would get a better control even then, right? It would be like 1 plus 1 over log or 1 over root log of the expected value, but oftentimes you can have a much better control. And what we'll see in the next class is the next lecture is we'll try these inequalities for simple examples that we understand, and we'll see when the logarithmic factor belongs or not, and we will see a suggestion that it seems actually that this weak variance may help tell us when it is that the logarithmic factor belongs or not. And this is a conjecture that I personally really like, and so I'll show this in the next lecture. And so we'll talk a little bit more about this parameter and this one, and uncommutative kinship, and try it in a few examples and get a better feel for when it is tight and when it's not tight. All right, thank you.